Welcome to Unshielded, the podcast where we explore the cutting edge of blockchain, data protection, and the quest for a more equitable and accessible internet. Today, we have a truly special guest joining us. I'd like to welcome Thomas Kerber, technical architect at Midnight. Thomas brings a wealth of experience in computer security and blockchain technology with a significant background in research and development at Input Output Global. His work on the Kachina Protocol and its evolution into Midnight has been groundbreaking in the field of smart contracts. And in this episode, we'll delve into the novelty and evolution of Kachina, the unique challenges and opportunities for developers working with zero-knowledge proofs, and the benefits of building dApps on Midnight. We'll also get into an in-depth demo of a round-trip transaction on Midnight and discuss how these innovations are shaping the future of data protection and decentralized applications, or dApps. Thanks for joining us, Thomas. How are you doing today?
I'm good, thanks. Thanks for having me.
Appreciate having you here on the Unshielded podcast. I know you're a busy man. I know you've got a lot going on, but we're very, very lucky to have you. As someone deeply involved in the development and innovation of blockchain tech, what excites you most about the potential of data protecting smart contracts?
I think it's not exactly a secret that blockchain hasn't seen the adoption that a lot of people would have hoped for it. And in my mind, there are several possible reasons for that. But I think one of the biggest is people need privacy. And it's just many applications that you might want to run on a blockchain. If you don't get privacy, it's a no-starter. So honestly, I don't know what applications we'll get out of this, but my hope is that it brings blockchain technology closer to a place we hoped it would have been anyway.
And thinking back to your research, your PhD, and into Kachina, what motivated you to focus on this particular area at the start?
In part, it was that. So in part, I looked at where blockchain technology was at the time. And to my mind, there were two major unsolved problems at the time. One of them was privacy. And I won't claim that I've solved privacy. I think it's a tangled knot of problems, and you can make progress on it, but you can't solve it properly. But I think we've gone some ways of the way since I started working on it. And the other one was scalability, and I think that's also a problem that is still being fought with in various ways and in various domains. Privacy seemed more interesting, so that's why I went that direction.
And if we get things right, if we see Kachina and if we see data protecting smart contracts and blockchains being used more widely as the technology becomes more fit for purpose, what do you see as the outcome of that in terms of how people might interact with each other or with data in general? What are you hoping for?
I don't think things will turn out as I hope. But ideally, I think that this could pave a way to having self-sovereign data and moving away from a world where there are large data collecting agencies that know everything about you and advertise to you, using that to a world where you share only what you need to and don't share it beyond where you need to. I think zero-knowledge proofs are quite useful in that respect because they reduce the amount of data that you need to share. Even if you do want to do things with that data, you don't necessarily need to reveal it.
Transparency where it's required and data protection and privacy everywhere else. Let's get into the meat of the discussion. Let's kick it off. Could you provide a little bit of an overview of the Kachina model for smart contracts and talk us through what makes it novel compared to some more traditional or well-known smart contract frameworks?
I think you kind of incidentally just summarized it with transparency where required. So one of the key insights of Kachina is that if you have a blockchain system, by necessity, you have some transparency. The blockchain is a public thing. Everyone can see what happens there. So the question then becomes, what does it mean to have privacy in a public system? The conclusion that we came to is that you're public about what has happened, but that you're not public about how you got there. And Kachina really exemplifies that split, that you are explicit in what the state of things are in public, but that you also have things that you keep secret and you don't tell other people. and that you use those to change the state that others can see without revealing why or how you did that change. Yeah, that's kind of the key part of Kachina, is to evolve these things together, but not show how you're evolving them. And I think that differs from the more traditional model of smart contracts, where you only have this public state that's evolving. And the inputs, the reason or how it's evolving and why it's evolving that way is also public.
And coming back to the beginning, obviously there's a significant amount of research that you've put into Kachina along with others. How did the concept come about? What were some of the principles you started with when you started going through its development?
Initially, I think the concept was, well, what if we had a smart contract platform like Ethereum and we tacked on zero-knowledge proofs and privacy? It sounds very simplistic, and it's one of the things that, while working through it, we quickly realized is that you can simplify a lot of the model, or that you can, really boil it down to the core parts, and that the public smart contract part still plays an important role, but that the interesting thing is more the orchestration between what you're doing in zero-knowledge proofs and what you're doing in public on-chain.
And since the research has been complete, it's then about putting that research into practice. And so could you talk us through how has the Kachina Protocol evolved from the early days of the research into implementation in the Midnight Network? Could you talk us through kind of the key phases of evolution, or were there any particular breakthroughs along the way?
I'm not sure I'd use the word breakthrough, but there are certainly some changes to what you would read if you read the Kachina research paper and what we're delivering in Midnight today. And I think a lot of them have to do with practicality. So, for example, Kachina had no notion of funds in the system. There was no currency. There was no way to pay fees. That was just out of scope. But in practice, you need to do this. And if you have, some token, you want to be able to handle that in contracts and interact with it. A lot of things happen with just how to interact between smart contracts and tokens that we added to the system. I think another aspect, which I don't want to emphasize too much because it's not something we have actually released today, but which we have certainly designed around, is the desire to interact between multiple contracts, that you want to have one contract be able to call another and be able to build up interactive systems with smart contracts. Moreover, not just interactive systems, but the original Kachina paper deals with a single contract. So just having multiple contracts that can be deployed and work in isolation was something that we had to work around. I think another major difference is we had to take denial of service attacks seriously, and we had to decide what the on-chain execution model looks like and how to cost for it. We had to do something like a gas model and manage what changes are sensible and are allowed, whereas in Kachina, we just said, you write a function and you apply it. It's a very different level of concern.
You can see immediately the difference between, I don't want to say theoretical, but certainly in research versus in the practical application of technology that is designed to host value and important, significant assets, or be part of a working, practical, interoperable system. Another thing that I know I've heard you speak about before is Snarks and the concept of Snark upgradability. Could you talk us through that and how Snark upgradability has been included in your design for Midnight?
Yeah, so this is a very tricky topic, and I want to be clear that I don't think we have solved it perfectly yet. I think we're taking the first approximation to addressing a concern that we know will be a problem in the future. The key problem is, so we have our zero-knowledge proof system, which is based on ZK Snarks. And if you're at all aware with the ZK Snark space, you'll know that there are many proof systems to choose from. And seemingly every other month, there's a new hot topic. There's something out there which is faster and better and does this thing in a different way. So one of the challenges we have with Midnight is, at some point, we'll inevitably want to pick a different proof system. We'll want to go for a new hot Snark that does things in a different and better way, which ordinarily isn't too much of a problem. But since the zero-knowledge proofs are part of our transaction model and part of our smart contract model. We now have the challenge of what happens with contracts people have written in the past, and how do those work with a new proof system? Essentially, it's a situation where you can't do much in many situations, where you have to kind of rely on someone being able to recompile the contract and use it with the new version of the proof system, or support the proof system indefinitely. Right now, we're too early to support a proof system indefinitely. We're not at the point where we want to lock something in permanently. So what we've built in is a basic functionality to allow upgrading of contracts. And our hope is for that to become more nuanced and more reliable over time, as well as finding others, working on new solutions to this problem while we're doing that. There is, of course, a danger with upgrading contracts, which is if you can upgrade a contract, you can also upgrade it maliciously. You can put in code that you say, I take all the money out of it. And that's also not ideal. So we're still feeling out the space. And I think it's good that Midnight is still fairly early, because it leaves us room to figure out what people want on this and to reach compromises, because it seems to me like a place where we will have to compromise one way or another.
I think all technology systems are a compromise of various different requirements, but I think it's inspiring to hear that, at least from what we've seen in blockchain and Web3 so far, Midnight and you and the team are trying to push forward some of the most important things, which relates to data protection, scalability, upgradability, and so on. While we get closer towards the demo, one of the core premises of Midnight is data protection. For those people who may be less familiar with Midnight's architecture or some of the technical components behind it, could you talk a little bit about how zero-knowledge proofs enable sharing of, or protection rather, of sensitive data, and keeping that while also allowing meaningful transactions on smart contracts to work?
Yeah, so I kind of glossed over it before when I was explaining the basics of Kachina. And I guess it helps to give a very high-level overview of what zero-knowledge proofs actually do, because I guess not everyone here necessarily has that background. It's hard to say this as a soundbite without it coming off as magic. So I'll try to be a little more concrete than you might hear in other places. What zero-knowledge proofs let you do is cryptographically prove that some program will produce a certain output without revealing the inputs to that program. And there are a bunch of restrictions on how that program can look like and what it can do. But the essential gist of Midnight Smart Contract model is when you're writing your contract, that's the program whose inputs are not going to be revealed. And the outputs of that program are a change that program will perform on the on-chain state. I think in the demo, I'll go a little bit into what those changes look like. It's not necessarily going to be the most digestible at that level, because I'm going fairly deep into the guts. But the idea is that you show something that changes about the public state. So that might be as simple as a counter incrementing, or it might be a more complex sequence of changes.
So developing with zero-knowledge proofs can be a bit of a depart from traditional programming. Could you take us through what are some of the hurdles that developers may face, or maybe some of the slight differences when working with zero-knowledge proofs as opposed to more traditional programming methods?
Yeah, so one of the tricky parts with zero-knowledge proofs is because of how the technology works, it's more like designing hardware chips than it is writing traditional programs, by which I mean you're really using up resources whenever you do something, and there's no concept of looping or recursion or constructs that you might be more familiar with. Now, I'm simplifying a little bit. There are zero-knowledge languages that do have looping and recursion, but they usually pay a very high overhead to achieve that. And it's not something that we're currently doing in Midnight. So what we're currently doing is more towards the taking the contracts that you're writing, and conceptually you're building conceptual piece of hardware that corresponds to that we know how to prove things about. And one of the tricky parts is that developers are very used to working with dynamically sized objects and working with variably sized loops, et cetera, et cetera. And this is something which, you kind of have to unlearn. You kind of have to figure out, no, I can do this with a fixed size thing here, or that you impose bounds on how long you want to do certain things. And it does limit what you can do. Now, the other side, I think, is zero-knowledge proofs are still fairly new, and there's not that much tooling and not that many languages around it. So one of the things that is fairly common is that it's actually just hard because of the lack of tooling support. And in Midnight, we've put a great deal of effort into trying to make it developer-friendly, to have a language that is relatively familiar to developers, that they can write things for the most part how they'd expect, and then interact with it for the most part how they'd expect. Whereas in a lot of other systems, it's much more low level and much more to the level where you actually are building up that hardware and you're expected to know it's hardware and know to interact with it like it's hardware. And that's especially true for one thing which is quite crucial for Midnight, where you have these stateful interactions with the contract states directly written in your contracts. And this is part of the reason why we did our own language instead of picking something up that someone else had written, is because there was just no way to do this interactivity in most of these languages. So the fact that we have interactivity, to my mind, is one of the benefits that we provide, and what makes it slightly more approachable than other solutions here.
Very good. So while it is still a relatively new domain, trying to lower the barrier to adoption, trying to make it as easy as possible for programmers who are used to changing frameworks and used to changing languages from time to time. So hopefully not deemed to be too much of a hurdle, but still a new domain to explore and still relatively early. Let's get into the good stuff. Let's get into the demo. What I've asked for you to do today is, could you take us to a typical, for want of a better phrase, round trip transaction on Midnight, from start to finish, the steps involved from the initial contract maybe to the final verification?
All right. So, when I looked into this, I was not completely sure how to approach round trip. So I'll tell you what I've done. I'm going to start by walking through one of our internal test contracts, which is a small DAO contract. And I'm going to then go through the stages that a transaction takes as it's being built up, and then applied against the ledger. Now, interestingly, I'm not actually going to show the proving and verification parts, because there's not that much visibly going on here. I will briefly say what those parts are doing, but just full disclosure, this demo has no proving or technically verification in it. It does have application of the contract, which I guess you can view as part of the verification if you want. So to start with, I'm going to go into this contract. So as I mentioned, let me just make that full screen. As I mentioned, this contract is essentially a small DAO that we use for testing. So it's a toy DAO. There's various limitations of it. But what is interesting about it is that it does provide privacy for who voted for what and in what direction they voted. And it does that with a commit reveal voting scheme and using commitments and nullifiers to prevent linking of the votes to the voters, essentially. I'm not going to go too much into the technicalities of that because I want to focus more on the transaction. And in particular, I'm going to go through what was it again? I'm going to go through the commit phase of the voting, which is where the initial ballot is being cast. So in this vote, it's just a yes or no vote, so it's just a Boolean ballot. And importantly, I'm going to try to convince you that the which direction I voted is not going to be revealed on chain. So I am going to start my little hack together demo script here, and this is going to output various stages that we're going through during the transaction processing. So initially, what I've constructed here is just a ledger state initialized with this contract deployed and nothing else, just for the purposes of testing. And this is a point to go over also what is visible on chain and what is what makes up the public part of the state. And if you're familiar with Compact, then you'll know that these ledger declarations are what should be publicly visible on chain, but they're not visible in the way they are in Compact. They're visible in a more bytecode-like form. So this organizer cell here becomes this mess up here. If you know how to read this, which I do, it's not too different, but if you don't, then this might very well look like nonsense. But yeah, importantly, these do correspond. So if you check check across these basically are representing the same thing, just in a different format. So the next step now is, and I'll just quickly jump over here to the JavaScript output of the contract, which is this one. Let's take that whole screen again. So if you've used Compact before, you might be familiar with these JavaScript outputs. This is the type declaration for the output of this particular contract. And you'll know that you can construct contract objects and then interact with the circuits on that contract. It's worth mentioning that at the moment I'm not using Midnight.js for this, just because I'm keeping the things I'm using in this demo small. And what I have now done is I've run this vote commit entry point in the JavaScript output. I've passed it my ballot, and at this point I'm voting for yes. I want to vote. I mean, there's no actual proposal, so it doesn't mean anything either way. But I have voted, and one of the things that it gives us as an output is proof data. And this is everything that is needed essentially to construct the corresponding transaction. That includes the input to this circuit. So if we go back to the original circuit up here, this is literally just the input to this function call, essentially, encoded again in a low-level way. The output is also captured here, but it returns void, so there's actually nothing in there. And then, importantly, this public transcript is the only thing that will actually appear on chain. This is encoding a program that gets run against the contract state up here once the transaction is run. I'm not going to go through what this program does in detail. I'm just going to briefly mention that these roughly correspond to queries that are run against these ledger objects. So things like this committed.member check will be compiled into a sequence of operations here that perform that check in public against the state. Then we also have a record of what these witness functions output during the call of this this vote commit execution. So there's various things that are going on here. We're getting the state that we're in locally, whether we believe we've already voted or not. We're getting our own secret key, which we need to demonstrate that we're eligible to vote. And we're getting a Merkle path to demonstrate that we're eligible to vote. And that, this is the secret key. This is sensitive data. You do not want to reveal this. unless, of course, you're running a demo and it's all without value. And this is the path to the public key. There's less danger of revealing this, although it still has downsides. If you reveal this, you lose anonymity of which public key voted. In this case, that doesn't actually matter because there's only one eligible public key. But again, that's kind of beside the point. So then the next step is you use this to assemble a prototype of a transaction, where you now have a couple of new things in this. You have the contract address that's being called. You have information about which entry point is being called, what the keys associated are, and there's some processing going on where this public transcript up here is put in a different format. It's annotated with an estimated gas cost. It's annotated with effects, which I was talking about previously, that there are things with how we interact with our with our shielded token system. But by and large, it's the same transcript, just in a different format. And similar with the private transcript outputs, the input and output, these are the same things as in the proof data up here, just in a different format in a different place. And yeah, there's some additional things that I won't go into related to proving and cross-contract calls. Once you have that, you can essentially send that off to proving, and once you do proving, you can get a real transaction out of that. Now, I have not done proving here. I've essentially just said ignore that, don't do that. But it's worth pointing out what proving actually does. So importantly, proving uses these ZKIR outputs, which are low-level bytecode, is again essentially representing this specific function on the contract in a format that is directly evaluatable as a zero-knowledge circuit. And importantly, this is both equivalent to the contract you originally wrote, but importantly also, you can directly check this against the proof data. So you don't need to run any of the JavaScript code again. You don't need to be concerned about the witness functions or the state of the contract. You just need to know the proof data and the ZKR code, and then you can check that they match, that it actually does what it said it should do. That's what the zero-knowledge proof does. It is a proof that the proof data you've supplied is correct with respect to the ZKIR output. And we've set that up so that the ZKIR output ensures that the rules you wrote in the contract are being followed. Now, once that proof goes through, all of the proof data is essentially forgotten, with the exception of the public transcript. So this part that is saying how to update the public state, that is saying how each of the ledger calls is being applied, that is still present. So in particular, this committed.member check is still happening. The Merkle tree root check for eligible voters is still happening. And your vote finally getting inserted is still happening. But how these values are derived during this, that's not something that's visible in this transcript. These values are just strings that appear in the transaction with no explanation. And importantly, that includes, so for example, in the case of this commitment, this is a commitment to how you voted, which means it contains your vote, but it does not reveal it. And I think, I don't know which of these pushes it is. I'd have to dig a little deeper to figure that out. But one of these is going to be that commitment of the vote, which as a cryptographer, I have to say that manually looking at it, you can't tell whether it is revealing it or not. But I would like to assure you that it is not revealing in which direction I voted at this stage. So this is what a transaction looks like after proving. And what happens after that is two parts of checks. The first check is a well-formedness check, during which ordinarily proofs get verified, and things, various other things get checked, like that the transaction is actually well-funded, and that it's internally consistent. And in this case, if I just do it as is, it's going to tell me, well, the transaction isn't well-funded because I didn't bother funding it with anything. There's a part which says which inputs and outputs it has. I haven't bothered in this demo. But if I turn off the funding check, then this silently passes as a check. And then the second part is applying the transaction to the ledger state. Now, transaction application can succeed or fail, or it can partially succeed, but I'm not going to go into that in detail. In this case, the application says it succeeded, and if you look at the contract state after application, there's a couple of things here that have changed from the initial state up here. So in particular, if we go back and look at these ledger fields, one of the things that should really have changed is that the committed votes field should now have our vote in it. And if we find this field, it's this one here. We note that initially there were no votes that committed. And after we have run this, I believe it's this one, there is now one committed vote in there, which is our vote. And again, it's not revealing what it is at this stage. The other thing that's changed is, I believe, this map here, is the committed map, and this is essentially what prevents us from voting twice, because we're trying to check whether we have already committed our vote when we submit this transaction, and if it's in there, then we reject the transaction. That's something we can actually see. If I try to run the same transaction again, then it gives me a failure. And it says it gives a rather obscure error. The reason it's obscure is because the ledger has no knowledge of the contract. It doesn't know what it means, what it means, what it's executing, essentially. But what it does know that it should run this program. And while running this program, it does a bunch of things. But one of the things it does is it checks whether or not we are already in this committed set. And in this case, it's making an assertion to say it should be false. But the actual execution gives us true. And that is why this execution gets rejected in this case. So this is, where it can get a little bit subtle with our contract model is there is this possibility of a mismatch between what happens locally and then what happens on chain, because things could have changed on chain in the meantime. That's all I wanted to show for today.
A fantastic demo, Thomas. Thank you very much for that. And just a little microcosm there of some of the differences of working with zero knowledge as opposed to other traditional programs is debugging and error logging. If the system doesn't know if the system doesn't know the contract, it doesn't know the details, the quality or granularity of the errors may be very different. And so an interesting insight there for sure.
The number of times I've had to explain to people that I'm sorry, I can't give them that debug information because it doesn't exist is, it's not trivial.
Something for us to work on with UX for sure, but a very, very interesting demo nonetheless. Maybe just to summarize briefly, for traditional developers accustomed to other smart contract approaches or other ways of developing and progressing decentralized applications, what would be some of the main things that we saw in the demo there that are maybe different or better than what they would be used to using today?
So I think one of the interesting things is most of your program does not reach on-chain. So you could have a very complex program that doesn't interact much with the outside world. You could have a program that is doing a lot of internal logic and then maybe says yes or no at the end, or does a small number of things. And that could end up being, as far as the transaction is concerned, and as far as the on-chain component is concerned, it could end up being almost trivial. Now, it's not going to be every program, but I do think a lot of programs on traditional smart contract platforms spend a lot of time doing validation, which could be done in a zero-knowledge proof instead.
Thanks for that, Thomas. And as we wrap up our discussion, looking forward, how do you foresee the field of data protecting smart contracts evolving over the next few years? You mentioned that we're still very, very early. Midnight is still very, very early in the hands of developers and the developer community. What are you looking forward to?
Honestly, I'm not sure how the next couple of years are going to turn out. I think what's going to be really interesting is once the community really gets their teeth into things and starts looking at building contract standards and interactions between shielded smart contracts, there's going to be an interesting burst of things that people figure out are possible that we didn't consider before. And quite frankly, I probably wouldn't be able to consider at this point. It's a bit of a cop-out, but I don't know how to answer that. And I really just want to wait and see as well, because I'm not sure what we're going to see. And I hope that we see an explosion of interesting applications, because we are certainly giving people the tools to enable that.
I would agree. I think this is the moment where some of the blockers to seeing more widespread adoption of smart contracts and on-chain activity is the ability to shield sensitive information, whether that's intellectual property, individuals' data, value data, market data, whatever it might be. We've already seen a significant amount of interest in decentralized technology from enterprises, from governments, from the Web3 community more broadly, but they have been hindered by public data being too public and previous privacy solutions being too private or not compliant. And so, like you said, I think we've provided the basis for that innovation. And I guess that's part of the challenge of being somebody innovating on platforms is you're providing the platform rather than building a specific use case. So I'm sure it will come, and I'm excited to see what comes next. As we close, what's one piece of advice you would give to our listeners as they're looking at building with zero knowledge or data protecting smart contracts on Midnight?
I think the one piece of advice I want to give is kind of two-pronged. And it's that on the one hand, I know from experience, and because I have a background in this, that building systems that actually preserve notions of privacy is hard. It's very easy to accidentally reveal things that you didn't want to. And it's very easy to create correlators. And sometimes it can feel like you need to be an expert to get started. And I think to some extent, you need to be an expert if you're going to make explicit assertions over what privacy you're providing. But there's a flip side to this, which is anything you do will be an improvement over the existing public state. So, the other side of it is just add something and it'll be better than the status quo. So be careful in what you're claiming, because it's very easy to overpromise, but also don't be afraid to try. It's not like you have to have a PhD in cryptography to write your first contract.
And that wraps up our enlightening discussion with Thomas Kerber, technical architect at Midnight. We've gained incredible insights into the foundations of data protecting smart contracts and the evolution of the Kachina Protocol. Thomas, thank you so much for joining us and for sharing your expertise. And for those listening, if you've enjoyed this episode, be sure to subscribe, rate, and leave a review on your favorite podcast platform. And don't forget to follow us on social media for the latest updates and more exciting conversations in the world of blockchain and data protection. Unshielded is brought to you by Midnight. To find out more about how the Midnight Network is helping everyone to build a more equitable and accessible internet, visit our website at midnight.network. And remember to search Unshielded on Apple Podcasts, YouTube, Spotify, or wherever you get your podcasts, and be sure to subscribe so you'll never miss an episode.